We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
My name is Hiren Patel, working as Assistant Professor in Mahatma Gandhi Institute of Technical Education and Research Center, NAVSARI in Mechanical Engineering Department. In my previous lecture, we have learned about the reverse Carnot cycle and Bell-Coleman cycle. Today, in this video lecture, we are going to see how the examples will be calculated on the basis of the theory of reverse Carnot cycle and Bell-Coleman cycle. So starting with the first example, so 1.5 kilowatt per ton of refrigeration is required to maintain the temperature of minus 40 degrees Celsius in the refrigerator. If the refrigeration cycle works on Carnot cycle, determine the following: first, COP of the cycle; second, temperature of the sink; third, heat rejected to the sink per ton of refrigeration; and fourth, heat supplied and EPR if the cycle is used as a heat pump. So here we need to find out the 4 different data. Now first we need to derive the data which is given into the example. So if we read sentence by sentence, then we can find out first, that is 1.5 kilowatt and per ton of refrigeration. So here there are 2 datas are given, that is WR, that is 1.5 kilowatt, that is the work required, and second thing is Q, or we can say Q1 or Q, that is the refrigerating effect or refrigerating capacity, that is 1 TR, 1 ton of refrigeration. Now it is required to maintain the temperature of minus 40 degrees Celsius. So temperature T1 that need to be required at minus 40 degree Celsius. So if we convert it in Kelvin, then it is equal to 233 Kelvin. Remember, whenever you are calculating the example for the Carnot cycle, reverse Carnot cycle or Bell-Coleman cycle, you need to convert the temperature into the Kelvin from the Celsius. Next, so another data are not given, and we need to find out COP of the system, then temperature of the sink, and that is T2, then heat rejected, that is Q2, and EPR, and heat supplied, that will be the heat rejected to the sink. So that much data we need to find out. So these are the data that is given into the example, and we need to find out these are the data. So if we go for the cycle, then first Carnot cycle, that is 1, 2, 3 and 4. So 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So this is the Carnot cycle TS diagram. Now if we consider the heat engine, then work required, that is work need to be given. Here T1, that is the cold body, and sink, that is T2. Here is the refrigerator. So Q1, that is the heat need to be absorbed, and Q2, that is the heat to be rejected. If heat is need to be rejected in the refrigerator, then in heat pump it is the heat supply. So that is the heat supply here. So now first we need to find out the COP of the refrigerant. So the COP of the refrigerant will be Q1 by WR, that is 210 divided by 90. Why 210 only? Because Q1 is 1 TR and 1 TR is equal to 210 joule per kilojoule per minute. Okay, so 210 divided by 90, and 90, that is the work done. How? That is WR is equal to 1.5 kilowatt. If we convert it into the kilojoule per minute, then 1.5 kilojoule per second, and that is equal to 1.5 into 60, and that is 90 kilojoule per minute. So the WR is 90. So if I find out the COP, then it is 2.33. So this is our first answer. Now if we see, then COP of the refrigerant can also be calculated by T1 upon T2 minus T1. So if we take COP that we have find out, that is 2.33, is equal to T1, that is also already given, that is 233 Kelvin. So 233 divided by T2 minus 233, then T2 can be calculated from this. So T2 minus 233 is equal to 233 divided by 2.33, or T2 is equal to 233 divided by 2.33 plus 233. So T2 will be equal to 333 Kelvin, and if we convert it into Celsius, then it will be equal to 60 degree Celsius, that is minus 273. So this will be our second answer. Next, that is heat rejected into the sink, that is Q2. So Q2 will be Q1 plus WR. If we see here, then Q2 will be Q1 plus WR. So Q1, that is already given, that is 210, and WR, that is also given, that is 1.5 kilowatt, and we have converted it to the 90 kilojoule per minute, so it is equal to 90. So total will be 300 kilojoule per minute, and this will be our third answer. And last answer, that is heat supplied and EPR if the cycle is used as a heat pump. Here, fourth one, heat supplied and EPR if the cycle is used as a heat pump. So for that, we have Q2, and that Q2 is 300 kilojoule per minute, and that is the our answer for the heat supplied to the cycle, heat supplied into the cycle when we are using it as a heat pump. And EPR, that is equal to COP of refrigeration plus 1, or we can say that it is the efficiency of heat pump refrigerator, and that is equal to COP of refrigeration plus 1, and that is equal to 2.33 plus 1, and it is equal to 3.33. So this is our last answer. So this is the full example solution. So our next example is for Bell-Coleman cycle. So in a refrigeration plant working on Bell-Coleman cycle, the air is compressed to 5 bar from 1 bar. Its initial temperature is 10 degrees Celsius. After compression, the air is cooled up to 20 degrees Celsius in a cooler before expanding back to the pressure of 1 bar. So determine the theoretical COP of the plant and net refrigerating effect. CP is given and CV is given. So here, if we find out the data, then first, before that, if we draw the cycle, Bell-Coleman cycle on PV diagram and TS diagram, so it is easy to find out the data. So PV diagram, if we draw, one, two, 3 and 4. So that is our PV diagram, and if we see TS diagram, then it will be something like this: 1, 2, 3 and 4. So here we are having T4, T1, okay, this is TS diagram, T3, T2, and in PV diagram this is P1, that is equal to P4, and here P2, that is equal to P3. So these are the diagram. So from the given example, if we calculate, the air is compressed to 5 bar from 1 bar. So here P1, P4, that is equal to 1 bar, and here P2 equal to P3 is that is 5 bar. The initial temperature is 10 degrees Celsius, and that is the first T1, that is 10 degrees Celsius. After compression, the air is cooled up to 20 degrees Celsius. So after compression, that is after compression point is 2, and after cooling point is 3. So T3 that is equal to 20 degrees Celsius. Okay, so these are the data. So if we note down the data, then P1 is equal to P4, that is equal to 1 bar. P2 that is equal to P3 equal to 5 bar. Then T1 is equal to 10 degrees Celsius, and converting to the Kelvin, that is equal to 283 Kelvin. T3 20 degrees Celsius, converting to Kelvin, 293 Kelvin. And Cp that is 1.005 kilojoule per kg Kelvin, and Cv that is 0.718 kilojoule per kg Kelvin. So these are the data given to us in the example. So first, starting with the gamma. So gamma is equal to Cp by Cv, and that is equal to 1.005 divided by 0.718, and that is equal to 1.4. Now for the isentropic compression process 1 to 2, here this is the isentropic compression. So for isentropic compression process, T2 by T1 that is equal to P2 by P1 whole raised to gamma minus 1 upon gamma. These are the standard equation of gas dynamics that is applied over here into the air refrigeration cycle. It is already discussed in theoretical portion. For that you have to see my previous video of the Bell-Coleman cycle. So P2 by P1, the P2 and P1 are already available with us. So 5 by 1 whole raised to 1.4 minus 1 divided by 1.4, and that is equal to 1.584. So T2 by T1 is equal to 1.584. Same as if we calculate for process 3 to 4, that is also isentropic process, and that is expansion process. So here 3 to 4 is the expansion process. So same, T3 by T4 that is equal to P3 by P4 whole raised to gamma minus 1 upon gamma, and that is equal to 5 by 1 raised to 1.4 minus 1 divided by 1.4, and it is same 584, that is T3 by T4. So here from this equation we can find out the different temperatures, that is T2 and T4. So if we go for the COP, then we require only T4. So here I am only calculating the T4, and that is equal to T3 divided by 1.584, and that is equal to 293 divided by 1.584, that is equal to 185 Kelvin. So the COP of the system can be calculated by T4 divided by T3 minus T4, that is equal to 185 divided by 293 minus 185, that is equal to 1.713. That is our answer. Now net refrigerating effect. So the refrigerating effect RE can be calculated by Cp delta T, that is Cp T1 minus T4, and we have already given the Cp, that is 1.005 kilojoule per kg Kelvin. So 1.005 into T1, that is 283 already given, minus T4 185 that we have found, so that is equal to 98.5 kilojoule per kg. So this is the second answer, that is the net refrigerating effect that need to be find out. So this is how we can find out the COP and net refrigerating effect that is required based on the Bell-Coleman cycle. Thank you for watching.